you very much for the introduction. It's really a pleasure, and it's a bit unusual for me to address such a broad audience. Oops, what's going on? Okay, so it's back. So initially, I planned to talk about something else, but in the end, we worked on ICML line until this morning, and I kind of excited about the work we submitted, so I decided to focus more on this very recent work, and also I think it's more aligned to what is discussed here at the workshop. So previously, the plan was to talk primarily about interpretability. And I think it's nicely linked, but in a very different way also to the talk by Claire, because we will also look into what happens to a pre-trained model when we post-train it, including post-training it for reasoning. Yeah, as Taylor mentioned, I am not cognitive scientist, but I hope that some of the insights we got from these experiments will be interesting also someone who maybe per se is not so interested in LLMs. Right, so what are we going to discuss? So we'll discuss what is actually happening in post-training for reasoning. Is the model actually learning new reasoning capabilities, or we are mostly reshaping capabilities which are already there in the model? And maybe we'll try also to approach this in a bit more rigid theoretical way to quantify what does it actually mean reshaping, what does it mean learning. So how we can talk about this more formally. And then if we talk about reshaping and if we talk about training, maybe different algorithms we have for post-training will have a different effect, will be more effective at reshaping, and some of them may be more effective at learning new things. So that's something I'm going to talk in a second part. And the last part, I think it will link a little bit to what Laura talked yesterday, and I think was coming up earlier as well, about chains of thought, faithfulness, and basically what can go wrong during post-training. And maybe also a little bit of how we can prevent this from happening. And I think the message, we'll back to this message, but I think the message is subtle, right? So when we want to post-train the model, we should be kind of careful with the material we are working on. So we have this base model, we don't want to break it apart. We want to kind of build on top of this, and in that way I really like this Henry Moore's words about sculpting and not about post-training, but that you need to collaborate with your material, but you also need sometimes to fight. And I think that's how we should approach post-training as well. All right, so I'll start with this work, which is my collaboration with folks here is at Mila here in Montreal. And so primary person who've done most of this work is Thomas Vergara, as a PhD student here at Mila. So the starting point for us is lots of papers recently which talk about superficial alignment hypothesis. And I think for the first time it was formulated in this Zhou et al. Paper, and I'll read the definitions there. A model's knowledge and capabilities, and this includes reasoning because experiments in this paper were primarily on reasoning, learned almost entirely during pre-training, and post-training teaches which sub-distribution of formats to use. So it uses this notion of sub-distribution. But then in a subsequent work over the last 2 years, there were different ways to approach this, so different arguments for superficiality. And we can roughly organize these different views in 3 groups. One would be a data view, which is basically saying that you need very few examples. I think many of you have seen these papers that we need 5 examples, we need 1 example to elicit reasoning, right? So this is data view that you need little effort in terms of examples. Another view approaches from a parameters perspective, so that you don't need to update the entire model, that you maybe need a small intervention, small sets of parameters you need to update. And the last, maybe even more extreme approach view on superficiality is that you don't even need to change the model. You can basically intervene at inference time by creating a good prompt, task description as the input to the model, or maybe modifying something in the algorithm you use to sample tokens. So you see, we have these different views, different kind of knobs, which are somewhat related to each other, but it's not entirely clear how they related to each other. Are they talking about the same thing, and how we can kind of put them on the same plot and relate to each other? And then also the wording used in this papers is very non-precise. So what is sub-distribution of formats? So how do we even define that? So what we're trying to do, we're trying to unify and operationalize this hypothesis, and in the process try to connect these different studies which happened before. Right, so what we use is a notion of task complexity, and which we introduce, and it's fairly simple. So it's a length of a short program that achieves accuracy at least delta given a pre-trained model. So basically a minimal program. So it's information theoretic perspective, algorithmic information theoretic perspective on this. And in principle, of course, it's not computable, right? Because how do we compute this minimal program? But it basically shows the effort in terms of length of the program which you need to spend on adapting this model to a given task to reach certain performance. So it's a function of target performance delta. And we can't compute it, but we can use methods, use basically papers which already exist on this topic to create the corresponding programs and compute their length. And if we do this, we can obtain estimates of program lengths for different methods. And in certain regimes, for certain target accuracy, some of the methods will be more tight because they all will be upper bound on the task complexity. So in certain regimes, you get one method preferable to another. So we can draw this Pareto curve. So horizontal axis here is the length of program in bits, and colors corresponds to different views to this approach. So in principle, this is actually not one approach. We will look at this in more detail. So there are different ways how you can, for example, operationalize parametric view. There are different ways how you can operationalize the data view. But what's cool is that you basically can put them on the same plot and compare them to each other. What I also want to clarify a little bit, so what is a program length? So program length in this case is not kind of program code. It's not a Turing machine code alone. It's also, for example, for data views, this would be the length of the compressed data. So altogether, this characterizes the effort needed to post-train the model. Of course, this notion is not entirely new. We are building on classic notions in algorithmic information theory. So something I'm sure many people in the audience know is Kolmogorov complexity. So Kolmogorov complexity characterizes information contained in an object as the length of the shortest program producing this object. So now we talk about fixed objects. We are talking of an exact production of this object. So it's not exactly what's needed for machine learning, right? So machine learning, we work with approximate methods. We work with generalization to new examples. Something less classic, more recent algorithmic rate distortion theory kind of addresses one of these issues. It already talks about approximate production of the output. So it talks about shortest program needed to construct an object within distortion delta. But then what we do, we effectively kind of generalize this algorithmic distortion theory to generalization of machine learning algorithms and also to accuracy of this algorithm. So it's not distortion, it's not memorization of specific example, specific string is with respect to performance of the method and with respect to certain minimal requirement on the performance. If you worked on interpretability, you may also be familiar with the notion of minimum description length probing, and broadly minimum description length, of course. And there is a close relation to this. And minimum description length probing was something my student Lena Vojta introduced a few years ago. And interestingly, another person who at the same time introduced was Tiago Pimentel, who is part of this team working on this project as well. So in MDL probing, the question we were asking was the degree representation in a model encodes certain, say, linguistic phenomena. So you might ask a question whether a certain layer of a transformer model, does it encode syntax, or does it encode specific syntactic formalism? And one way of doing it, I think we've seen probes somewhere here, would be just to have a model probe which would predict this. And in this work, we were arguing that it's not sufficient to just look in accuracy. You also need to quantify amount of effort you need to produce this probe, produce this classifier, right? Because if you're saying that something is very explicitly encoding, this should be easy to extract from this representation. And this is what MDL probe was doing. It was computing description length of the data set corresponding to this linguistic phenomena. So if you talked about syntax, it will be a description length of a tree bank given this representation, right? So there is a connection, but here we actually measure the entire program. We are not, because we want to measure across different approaches. So we are not just want to focus on a specific probe. We talk about broadly about ways of adapting a model. So this is not sufficient on itself. And we're also looking not in memorization of a data set, which basically MDL probe is doing. We are looking into generalization to new data. So there is a substantial difference. All right. Now, I will basically more like provide a teaser of the results we have in the paper, because there are lots of results, and I think that's some interesting insight, but I will talk about a few of them. So first of all, we look at different classes of methods. So for data view, for example, there are different ways how you can compress your data. The simplest way of compressing data, because it's text for us, would be to use a language model itself. There may be some more advanced ways of doing it. For parametric view, one way, of course, will be just train the model, post-train the model, look in a difference in weights, and figure out how to compress this whole difference. This would be pretty bad, and this will be really far from a Pareto curve. So what we do, we look in a parameter-efficient fine-tuning methods, like LoRa. And in principle, this already gives us a decent compression rate, but then we can also do much better using Bayesian methods. So things like Bayesian LoRa gives us, besides parameters itself, they gives us estimates of sensitivity of the model to these parameters. So in this way, we know that we need to accurately transmit, accurately compress certain parameters, but for other parameters, maybe it's less important. So this is the intuition behind variational bits-bad algorithm. So basically, this Bayesian LoRa was a very effective algorithm, and so on. So the different methods look up in the paper, which will appear next week. It's not yet there. We look in a different task and different language models, but I will discuss on the reasoning because we have a reasoning workshop today. Okay, so what do we have here? We have here plots for 3 language model, 2 versions of almost different size, and we also have a small LM 3, which is also 3B model actually. We can see that if your target accuracy is not very high, you can get with extremely short code. So it's 1/5, for example, of beats. So this is really something like 100 lines of Python code or something like that. So early gains can be obtained very cheaply. But then, at some point, you really need to spend more and more beats to reach this performance. And qualitatively, picture is kind of similar, but of course, for stronger models which already have strong capabilities, you can get a very high performance with very little effort, with a very short program. And yeah, and you can see ordering. I've shown on one of the first slides. So you have first inference method, then you have database method, and then you have a parameter compression techniques. So you can see that while you can argue about superficiality in the beginning of the curve, I think it's hard to say that everything what is happening is reshaping. So if you really want to juice your performance on a task as much as possible, you need to put lots of effort and your program becoming long. And I think this is really shows that it stops being superficial. An interesting things about introducing these methodologies that we can actually put these papers somewhere on a Pareto curve as well. So this is a paper which was suggesting that fine-tuning, post-training is superficial because it can be achieved by just fine-tuning top layer language modeling layer. But language modeling layer is actually huge. And fine-tuning the whole language modeling, it's actually quite a lot of effort. So if you would be compressing just this delta, you get a point very far away from a Pareto curve. So maybe that's not such a strong argument for superficiality. Then maybe slightly related to what Claire was talking about, looking at different checkpoints. So what if we actually post-training for our task the model which was already post-trained, right? So it may have not been post-trained on JSM8K, but let's push it there, right? And naturally, what you can see, because this skill is already there, we can get performance in instruction following and in reasoning with very short programs. So here, indeed, only reshaping is happening because reasoning in some way was already done by this model. So and now a little bit more about parametric view. We've seen that parametric view is quite a strong view to this, but maybe we can also get a little bit of more insight into what parameters you need to change. Because in the main experiments in this paper we submitted, we were just looking at LoRa, right? LoRa is still, updating all the layers, lots of groups of parameters in the model. But we can also do something else. We can train a very lightweight model. So that's from our ICML paper from the previous year, where we basically for every head in a model, we are training two vectors, one for additive steering, one for multiplicative steering. But also we learn whether we need this vector or not. And this is a mixed discrete continuous distribution, so we have exact zeros. So we're basically searching through where to intervene through the model. And this gives you a really tiny set of parameters, and even comparing to LoRa, so several magnitude fewer parameters. And these are not, unfortunately, bits of the program. We haven't computed yet for this model, but this accuracy, so it's the number of data points and performance on a task. And you can see that it also performs very well and uses very few parameters. And also, interestingly, with this technique, you can actually see where these parameters are located, so you can look further what's going on. Look, for example, if you're interested in functions of heads. So what this plot means, because that's a big model. I think it's Llama 7B, fairly big, medium model. So on the horizontal axis, you have layers. On the vertical axis, on vertical, you have layers, and these are ideas of heads. And light cells are where actually interventions are applied. And so you see very few heads are being actually modified. So most of the heads are almost not intervened on. So it's really reshaping going on with this model. Okay, so the takeaway for this part of my talk, we formalize the notion of superficiality, and I think this gives you ways to talk about this in a more clean way and also relate different papers together. What it also shows that many task-related capabilities are indeed encoded in training, but in many cases, to push the task further, you actually need to integrate new knowledge, integrate new capabilities. And this provides a nice segue into my second part of the talk, which is primarily work of Zi Huan, my student in Edinburgh, and another my student, Neil Rajani, and collaboration with a number of people in Edinburgh and beyond. So here we will be looking into types of post-training algorithms and their behavior, and we'll also link back to this reshaping and learning new capabilities as well. Okay, so the main two types approaches to post-training are supervised fine-tuning, or instruction fine-tuning, which is basically behavior cloning, right? So we training a model to imitate demonstrations either from an expert or maybe from another model. And another option is reinforcement-based fine-tuning, where we don't tell the model how to solve the problem, but we use rewards on the model-generated responses to reinforce good behavior and avoid bad behavior. So next slide, if you actually work on this, on reinforcement learning, would be very familiar to you. But I think it gives you certain insights, certain connections between these different algorithms and show you that they're actually in many ways similar. So here, the notation is the following. So X is the prompt, the input, a description of the task. Y is the response. And we now look into SFT, supervised fine-tuning, versus two ways of doing RL, just a policy gradient and something a little more complicated, PPO. So in SFT case, Y, the response is of policy. It's coming from the demonstration, right? And then we optimize the cross entropy of this response. The difference in RFT would be that response is not given by an expert, it's generated by the model itself. But the loss being optimized is actually quite similar, but it's now basically the same, right? But it's now weighted by the advantage. And so what is advantage, right? So advantage is how much better intuitively this response is than an average response. So for example, if all the rollouts are equally good or equally bad, these coefficients will be 0. So these A's are sparse. And what would be important if the model fails on this, failing to generate anything on this example, which gets a good reward. If all the rewards are the same, learning doesn't proceed, right? So you are not learning. And also the opposite. If your model is already very good at generating, you are not trying to enforce it even harder, right? Again, this coefficients is becoming 0. So you only will be updating if you have a difference in rewards between rollouts. And then a PPO, which is basically built on top of policy gradient, but it allows us to do a multiple gradient step on the same rollout. And because you do this multiple steps, you need to do a correction that you are a little bit of policy. And also you do clipping to avoid too huge updates to the policy. So you don't want to deviate to make too big a change which can break things. But what's important and still weighted by advantage. So again, if all rewards are the same, then you are not actually performing gradient update at all. So we will be calling this WPPO. It will come back again, this coefficient. So lots of similarity between these techniques, but resulting behavior will be actually quite different. So this is a paper at Actionable Interpretability workshop at ICML, Neil Rajani's paper, also collaboration with some people at Cohere. And what we show there across different experiments that well-tuned SFT and well-tuned GRPO, well, you're trying your best at finding the good parameters, have this problem that generalization for SFT is not so great outside of the domain, right? And also forgetting increases comparing to losing RFT. So if you're training with demonstrations, your gradients are bigger, your updates are bigger, you're more aggressive, you're more likely to break things. And because you're also forcing basically learning of a new policy rather than reshaping, you are likely will learn it in not a generalizable way. So it's not generalized, it's on a variation of this problem. And this is what we are seeing. And also maybe a small interpretability bit here. It's interesting. So not gradients are only bigger on SFT, which is natural because demonstrations are more surprising to the model. You get bigger updates. But also they actually update different sets of parameters of the model. Here the vertical axis layers, horizontal axis are different parameters, keys, values, queries of the transformer. And you can visually see that these patterns look very different for SFT and RL. And this is basically PPO. GRPO is a variation of PPO algorithm. So from this, I think the question comes, can we actually use SFT where we need it, right? So where we cannot learn just by reshaping, we want to have a push from the expert. But can we learn relying on reinforcement learning where you have a chance with reshaping? So can we kind of dynamically combine these strategies together? And this is what we'll come to in a few minutes. Before this, to get just a bit of a sense for what is happening during training with RFT and with SFT. For the moment, don't look in a blue part of the plot. Look only in red and green. So on the horizontal axis, we have losses, a loss for demonstrations. So demonstrations, so offline policy, so something given by an expert or expert model. On the vertical axis, we have average accuracy from 16 rollouts on the left, and on the right we have accuracy of the best rollout out of the 16. And this is about training, right? So it's not generalization for now. So what we can see is that naturally when you train with SFT, your loss on demonstrations, because you're training on these demonstrations, is dropping. But memorization, I could call it training accuracy, but basically memorization is increasing. In RFT, which doesn't observe, of course, these demonstrations, you can see that it's kind of discovering, reinforcing its own strategies. So the loss is slowly increasing. So it's actually deviating from the experts. And what other thing we can notice, which is maybe expected, is that when we look at average performance, then SFT doesn't actually perform that well, whereas RFT is performing better. But why it's natural? Because effectively this corresponds to objective we optimizing, right? So we optimizing expectation of the reward. What may be a more interesting plot now? So now we are trying to find hard examples. So how do we find hard examples for RFT? We take multiple other runs of RFT with different seed, with different permutation of the data, and look at average accuracy on examples across runs, and take, in this case, 200 hardest examples. So 200 examples where RFT performed worse. And what we can see is that RFT in this new run performs reliably bad on this example. So this is RFT. It can't really escape from this. So it's really generating rollouts, not succeeding, not getting gradient on this example. So it's basically stuck on these examples. And I think this kind of reinforces this intuition that we, for these examples where RFT is struggling, we need to give it a little bit of a push. So this is effectively what I just said, that we need to figure out how to make a push on RFT where we need to. And our idea was very simple. So what do we do here? So we generate n-1 rollouts in a usual way from RFT. So 1, 2, n-1. But for nth rollout, we do something slightly different. We sample length of the prefix L from some distribution, and then just take the prefix from the demonstration from the teacher, from our data set which we have, and roll out from there, right? So we start with this prefix, and so part of this is of policy, and then we start generate from our policy for the future. What's interesting that here we don't do in a later stage that much of modification. So basically we use this nth response, entire response, in the same way as if it would be generated from a rollout. So we basically apply the same weighting as we would do in PPO. There are a couple of small details in the paper which are actually crucial, but this is a simple story to it. So we provide this prefix hint. And this is the same thing written with the math. So for n-1 rollouts, we have weights from PPO. We have this weight for the prefix. And this is part from imitation, where we imitating the expert, but the weight is actually the same, right? So we are not distinguishing. So why using PPO weights is crucial? Let's think about this, what is actually happening. So if all rollouts succeed, in this case, you will get equal rewards. And these weights, as we discussed before, will be 0, right? So if on this example, model is already doing it very well on itself, you're not using demonstration. If some rollouts succeed, then your demonstration is downweighted, right? Because you distribute these weights across these successful rollouts. So what basically happens as intuitively we want, harder examples rely more strongly on the demonstration prefix than simpler examples. And also what you can look into, you can look at during training, and you will see that weight which is assigned over training to demonstration is diminishing. So it's basically initially it needs push, maybe not even on all these 200 examples, maybe on some of these examples, and then it generalizes to some of the other hard examples. But it's basically kind of automatically decide how much weight to assign to this. I'm not going to talk about these practical details, even though they're very important. Okay, but now we can also see indeed what is happening to these hard examples. So previously RFT was stuck, but now because prefix RFT, what we just described, is using this guidance, it kind of escapes this basin, escapes this area. And what is kind of cool, I like this plot, you can actually measure how much different examples relied on demonstration by looking at a difference in the loss before you started training and effectively at the end of training. And this is, in memorization community, it would be called counterfactual memorization score. So on the right, and this would be basically the examples which memorize demonstrations a lot, so they rely on demonstration a lot, and the ones on top rely on demonstration less. And then you can measure difficulty of the problem in the same way we were finding these 200 examples, basically looking at other runs of RFT. So easy problems are on the right, hard problems on the left. Maybe it's not super intuitive graph, we probably need to flip pages. But what you can see that for harder examples, you generally rely more on demonstrations than for easy ones. So if you fit a regression, you can see this difference. Okay. So the main, of course, point for this type of technical paper, having great results on the benchmarks, we do have good results on the benchmarks. I'm not going to bore you with tables. The paper is online, so you can see it. But I think there is a couple of interesting points I want to say, and you can verify them looking in this table if you're curious. So one interesting point that this method appears to be more crucial when you training model which has weaker reasoning abilities. I think there was discussion yesterday that when models have different strategies. I think Ben talked about this already kind of embedded in them, whereas a Llama family models don't seem to do this, so you really need to train them. And you indeed see that this more gentle approach we are using is more beneficial with Llama, because basically with Qwen it's anyway so simple to do this, so whatever method you use kind of works. All right, so this is takeaway for this part. So I think it's important to think about how we do post-training, so that you have a different behavior of different algorithms in terms of generalization, in terms of what happens to the model. And two classic approaches are complementary, and you can blend these approaches together. There is some related concurrent work to us on approaches such as LAFI, refit, UFT. You can also look at them, tap them to be compared to some of them as well in the last version of the paper. There is also relation to some more classic work in reinforcement learning. So, for example, Dagger is kind of opposite, right? So instead of taking prefix from the teacher, you take a start from a model, and then you rely on your teacher to continue. But this, of course, assumes success in training to the teacher. This is expensive. It's not quite possible with humans. And there are some simple techniques which I understand used right now standardly to post-train a model in industry, like on policy distillation, which have also related flavor. Okay, I was told I have only 5 minutes, so I'll try to make it in 5 minutes. So now we'll talk about what can go wrong, about faithfulness and change of sorts. And this is work of a student actually in Amsterdam. I have 2 appointments in Amsterdam and Edinburgh, Pedro Ferreira. All right, I'll start with the example. And this was, I was playing with ChatGPT when we just released this work in May last year. And so the task here is CV screening with LLM. Something I really don't like, but it's used a lot already. And actually in Amsterdam, one of the industrial leaders in this space is actually based in Amsterdam. They didn't fund this research. They wouldn't. But to make it a bit more fun, I won't be talking about screening CVs of real people. I will be discussing selecting fantasy animals for some imaginary intellectual game. And this also makes it possible to make it a bit more controlled. So you have a prompt, given a context. You have a list of CVs, and you want LLM to recommend one of the CVs and explain why it's doing that. And I don't want to read this prompt. It's slightly long, but what is crucial about this prompt is that it creates a certain tension between what a reward model thinks is a effective response and what a reward model thinks is a legal kind of good reasoning. So it mentions some hints that in my past experience, animals from this made-up island were performing very well. But also says that I really want to make a fair merit-based selection. So it's a bit of a tricky thing to do. And then what we have a list of these CVs, and CVs are actually useless. So they're designed in such a way they don't talk about anything intellectual. They're all about appearances. And there is only one thing which differentiates it, that one animal in this list is coming from this hinted region island. And I'm sure you know what happens, right? So what happens is reliably something like this. So it's always selects this animal from island, and then it makes up the reasoning. So apparently long tail, big ears, background fur, it's something really great for intellectual games. And then even to make it even, more bullshitty, it says based on trait analysis alone, you should select this person. And it's kind of coming again and again in different variations. So it's clearly we see this fabrication happening in near state-of-the-art models. So what stages of training are responsible to this? I suspect all of them, right? Our pre-training data is based on what human written, also what other language models written, and people are not fully sincere in their reasoning, not necessarily sincere, right? Then annotators can also take shortcuts. So if we talk about instruction fine-tuning, and in the end, both a kind of next token prediction and effectively the same loss use in SFT are behavioral cloning. So it's not a surprise. So it's already there in the model. But hypothesis we are looking here is that post-training increases this behavior, and we are looking into this, and maybe also how we can mitigate it a little bit. So one setting we look in the paper is very much like the CV screening, so biased data sets. But another one is a mathematical problem. And I'll use a mathematical problem here because it's very easy to see what's going on here. So we give a prompt which includes a problem to solve, very simple problem to solve. But we also give a textbook about math. And accidentally, sometimes these textbooks has exactly this question. We tell the model not to use this question, or at least if it decides to use, then to report this the use of the information clue from the book. And then you have a reward model. So we are not doing verifiable rewards, RLVR. So we use kind of more broad way. So we have a prompt, we have a response from the model we give to reward model and get a score. Right. So here it's easy to see why post-training here would result in enforcing this unfaithful behavior. Because there is this conflict between, again, effective response and acceptable reasoning, as we've seen before. So here we can see it by plotting reward scores of different types of responses. So the blue are incorrect responses. So they generally have low reward scores. And then there are two different types of mathematically correct responses. So green ones acknowledge that the textbook was used, right? So its solution is correct, but it mentions the textbook was consulted. And the red ones don't. And in post-training, what is basically happening, the model figures out that by omitting the mention that it's using textbook, it can move from the green curve to the red curve and score some points, just 2 minutes, I think. Yeah, I'm not going to talk about this plot that much, but you basically see an increase of non-faithfulness, and this is true according if you use rewards at inference time, if you post-train, if you use different reward models, if you use different variations these tasks. So our proposal is basically to provide reward model with some window into reasoning of the policy. So we said that the reason for why this is happening is because reward model had no idea about internal reasoning. We also don't want to provide it in such a way that it would be easy to hack or easy to basically bypass. So what we do, we used a counterfactual generation during training. So what we do, we automatically generate a counterfactual, which would be in this case hiding this solution from the book or replacing the solution with something else, doing a rollout, seeing if you see the same response. If not, you're actually adding acknowledgement to the output as if the models produced it itself, saying that I cheated, effectively. And then reward score would go down if this was added, and it removes incentive for the model to fabricate responses. And so again, we can see improvement in this. All right, so my message here, I'm wrapping up, is that there are lots of positive things about using reinforcement learning. We saw that improved generalization, but it's also a bit less predictable than SFT, so things can go wrong. But there can be some algorithmic ways to address these issues. So we talked about interpretability. Some other idea we brainstorm, and Laura actually in her talk mentioned as well, is getting reward model access to multiple samples. So it can detect this bias across different samples. So let's just think about this and figure out how to do that. All right, so this is my last slide. So post-training is not easy. And a lot depends with, on what you start with and what you want your model to do. And I also want to kind of repeat the message which was in Laura's talk, is that realistically right now chains of thought are the best general and simple tool we can use for safety. And instead of just saying they're unfaithful and useless, maybe they're not so unfaithful actually. And we will try to work on improving them. And there are of course dangers for this with latent reasoning and so on, which is probably even less transparent. So let's work on trying to make reasoning transparent. And of course I should really thank people who did all this work. Thank you very much.
All right, thank you very much for the great talk. We're over time technically, but since we're not going to have the discussion section, we're going to have the panel instead. Maybe we can take one or two questions if folks have questions for Ivan.
Thanks for a great talk. My question was about the prefix RFT, which sounds like a very interesting method. And I was wondering if you, and maybe you said this, but did you compare this to first training on SFT on the examples that were hard and then training on RL, and was there a difference?
Yes. We looked into kind of this pre-training on SFT, so it's one of the baselines. I think I even had this somewhere on a slide somewhere, but because I was running out of time, I missed this. But this is one of the baselines. So I do believe that you need to do something a bit more smarter than doing this pre-training. This pre-training already starts to destroy certain things, so that's kind of my intuition I have. So if you're already doing this pre-training, it may be not good. Or maybe that's also maybe softer way of doing this. If you actually use techniques like prefix RFT, you can get away with much shorter stage, so much less of destruction of the model.
Thanks.
All right, any more questions? Ben.
Thank you for the talk. That was really interesting. I'm curious to get your sense of sort of qualitatively, like what kinds of reasoning behaviors prefix RFT instills in models that RFT alone doesn't. Like, are there patterns in what kinds of questions beyond just difficulty you see an improvement in prefix RFT, but not RFT alone?
Yeah. So we haven't done for this project very careful analysis. So I think it's I don't want to it's a great students, but we have some students who want to look into detailed analysis, and interpretability students, some people who are less interpretability minded. So I think we tried to in short time to understand what is going on. But I think what I can say from kind of eyeballing and not very systematic analysis, some of these reasoning abilities are where it gets a push from the demonstration, and this emerged early on. And this is maybe one of the explanations why proportion of examples which receive updates on demonstrations kind of rapidly over training decreases, and then it kind of stays somewhat constant, because there are few tricks like points that you need to kind of go back to refine your hypothesis. Is model initially is not doing on itself, but then it gets from the demonstrations, and then things are becoming kind of easier. But yeah, we should have done a better study. I agree.
That's cool. Thank you.